So welcome to Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also see and appreciate the beauty in the simpler problems. So today's problem comes from the MIT 2024 Integration Bee Quarterfinals, number 4. And the second problem is what we'll be focusing on, which is the limit as n tends to infinity of the log to the base n of, in brackets, the integral from x equals to 0 to x equals to 1 of, open brackets, 1 minus x to the power 3, close bracket, to the power n, and then close bracket. So this whole problem is a very interesting problem. Before I proceed to the solution, I'd like to thank our subscribers. Thank you so much for your support. We are growing, and we don't take your support for granted. It's your support that motivates us to come here time and again. For our first-time visitors here, what we do at Everyday Mathematics is we just go around and about and look for problems that are interesting, and we try to solve them. We come back here and share the solutions with you. So we would really, really appreciate if you consider subscribing to our channel. To our friends who are coming back but haven't yet subscribed, we do really encourage you to consider subscribing to our channel. So this problem is interesting. And I would like to, as usual, I would like to substitute for the most complex term in this integral. That is x to the power 3. So what I do is I say let u be equal to x to the power 3 because I just want to create that abstraction that takes my mind away from the complexity in that expression. So what happens there is that du dx is the same as 3x squared. And thus, du dx is 3u to the power 2 over 3, because now we've expressed x squared in form of u. Because if you look at this, the cube root of u would be equal to x, and therefore x squared would be u to the power 1 over 3 times the power 2, which is u to the power 2 over 3. And so that's what we've obtained here. Now, dividing both sides by 3u to the power 2 over 3 results in du over 3 to the power 3u to the power 3 being something that would replace dx with. Now, as you can see, when x equals to 0, x to the power 3, or 0 to the power 3 is 0, so u is also 0. When x is equals to 1 cubed is the same as 1, and so u would also be 1. So the limits don't really change, and so our problem now becomes limit as n tending to infinity of the log the power to the base n, sorry, of the integral from x equals 0 to 1 of 1 to minus x to the power 3 to the power n is the same as limit as n tends to infinity of log the power n. The integral now becomes integral from u equals to 0 to u equals to 1, or 1 minus, in place of x to the power 3, we have u, so we have 1 minus u, close bracket, the power n, and in place of dx, we have du over 3 to the power u. 3 times u to the power 2 over 3. And we can decide to maybe pull out the 3 out, so we have 1 over 3 outside the integral sign, and then u can now be expressed, u to the power 2 over 3 can be expressed as u to the power negative 2 over 3. So this is good. We have that problem. Now, one other thing we could probably do is just express u first, then 1 minus u to the power n would follow. So we have a problem here that we can solve in 2 major ways. I'll begin by the simple way, the way that we are taught when we begin calculus, and we'll use the solution that involves integration by parts. Okay, so if that is our integral, we go forward and say, okay, we do have this 3 and u to the power negative 2 over 3. That's the same as the derivative of u to the power 1 over 3. So if you have an integral of capital U d capital V, the solution, as we are taught when you tackle integration by parts, is the product of capital U and capital V minus the integral of capital V d, the derivative of capital U. Okay, so in this situation, we have our V as u to the power 1 over 3, or the cube root of U. And then our capital U is 1 minus u to the power n. So our uv would be the product of u to the power 1 over 3 and 1 minus u to the power n, and applying the limits appropriately, plus now the derivative of u is now n goes down, derivative of u is -1, so the minus here and the negative that comes from differentiating 1 minus to the power n now would interact and we have a plus here. So we have the integral now of from 0 to 1 of 1 minus u to the power n minus 1 now, because we differentiated this 1 minus u to the power n. And then we've now kept v, and so v is u to the power 1 over 3. So limit as u tends to 1 on the upper limit, 1 minus 1 would be 0, so 0 times 1 here, that this entire thing becomes 0. And then limit as u tends to 0, when u equals to 0, so this becomes 0, so the entire thing goes to 0. This collapses to 0, right? And so the effective integral, this integral here is the same as n times the integral from u equals to 0 to equals to 1 of 1 minus u to the power n minus 1 times u to the power 1 over 3. We go to the same thing now. U to the power 1 over 3 is the same as 1 over 1 plus 1 over 3 times the derivative of u to the power 1 plus 1 over 3, right? And so we can now pull this constant out. So we have n over 1 plus 1 over 3 times the integral from u equals to 0 to 1 of 1 minus u to the power n minus 1 times the derivative of 1 plus 1 over 3. So again, we repeat the process here. We consider this as something that we could use integration by parts. So this becomes v, and this is u, and the process continues again. So now we have this constant out, and then so uv is 1 minus u to the power n minus 1 times u to the power 1 plus 1 over 3. And so continuing forward, the derivative of 1 minus u to the power n minus 1 is now n minus 1 times 1 minus u to the power n minus 2. So we've multiplied the n, now n minus 1, and the denominator remains the same. And so here again, as you can see, at the upper limit, when u equals to 1, this becomes 0. When u equals to 0, this becomes 0. So this entire thing again goes to 0. Now we continue down. Now the process continues. It continues. And again, we use integration by parts, right? And u to the power 1 plus 1 over 3 is the same as 1 over 2 plus 1 over 3, the derivative of u to the power 2 plus 1 over 3, right? And so the process continues on and on until we exhaust all the n's, right? So we have the process going on all the way until from n to 1, right? And then from 1 plus 1 over 3, 2 plus 1 over 3, all the way up to n plus 1 over 3. So this is our solution, because when now this n minus 2 degenerates to 0, this becomes 1, and we could easily now just integrate this u plus n minus 1 plus 1 over 3. And so that becomes an easy thing. So this is our answer for just the integral part. We haven't really tackled the limit. So how we could tackle this same integral in a different way is we could use the beta function. I've seen a lot of comments in our comment section, people encouraging us to use beta functions. This is something that probably would be common to anyone who has done applied mathematics, and that is the beta function of Z1 and Z2 is the integral from t equals to 0 to t equals to 1 up to the power Z minus 1, Z1 minus 1, bracket 1 minus t, Z2 minus 1. So we can express this in form of this, only that obviously here we have u and this is here we have t. So I can express negative 2 over 3 as 1 over 3 minus 1. And then 1 minus u to the power n can be expressed 1 minus u to the power n plus 1 minus 1. So Z1 here is a third and Z2 here is n plus 1. So this becomes now limit as n tends to infinity of log to the base n of 1 over 3, beta function of a third, and n plus 1. So beta function can be expressed as a combination of gamma functions, which is now the, keeping this a third here, gamma of function of 1 over 3, gamma function of n plus 1 over gamma function of 1 over 3 plus n plus 1. Right? So going forward, we can now express the gamma function of n plus 1 as n times the gamma function of n, and also the gamma function of third plus n plus 1 is the same as 1 over 3 plus n times the gamma function of 1 over 3 plus n, right? And this can go on and on and on and on until now this becomes 1. So in other words, gamma function of n plus 1 is the same as n factorial. And then for the denominator also, it becomes now 1 over 3 plus n all the way up to 1, or all the way up to the gamma function of a third, right? And now this gamma function of a third can cancel with the gamma function of a third here. And now we are left with a third times the n factorial over 1 over 3 times plus n, 1 over 3 times 1 over 3 times n minus 1, all the way up to 1 over 3 plus 1. Okay, so we've tackled the integral part, and it's obvious here that this constant here can, using the law of a logarithm, we can have two separate logs, because there's a multiplication here, so we can just add this, and with the limit n tending to infinity, this just becomes 0. So our focus now just becomes the limit of n tending to infinity of this second term here. In other words, n factorial over 1 over 3 plus n times 1 over 3 plus n minus 2 all the way to 1 over 3 plus 1. So we can then use Stirling's approximation, which tells us that if you have n factorial, this is can be approximated as n becomes larger with the square root of 2 pi n times n over e to the power n. And we can show that with the plot here. So we're plotting x factorial. On the x-axis, we have x. On the y-axis, we have x factorial. And as you can see, white is the plot of x factorial. And then blue is the plot of the Stirling approximation. As you can see, they really approximate each other very well. So we can use Stirling's approximation to now replace the factorial terms. So in other words, our problem now approximates to limit of n tending to infinity of the log the base n of 2 pi square root of 2 pi n times n over e to the power n in place of n factorial, and in place of the n 1 over 3 plus n quasi-factorial, we could use the same. So square root of 2 pi in bracket n plus 1 over 3 times n plus 1 over 3 over e to the power n plus 1 over 3. And so using the rules of logarithm, we can now separate the 2 pi's first of all can cancel out because these are constants. Those can go away. But now we can use the rules of logarithm to separate the numerator and the denominator. So for example, here, square root of n is the same as log to the base n of n, half on the other side, minus, since this also square root, a half of log the base n of n plus 1 over 3, plus, going back here, since this is the power, so this becomes a constant, so n times log the base n of n over e, minus, getting back the denominator, this power here becomes now something on the left-hand side of the natural log of the log to the base n, so n plus 1 over 3, log the base n of this n plus 1 over 3 over e, right? So if we express this problem this way, I think it's easy to really handle things. This is easy because it's the same as n, same base, so this becomes 1, right? And here, we could also, because the third is just a small increment over n, and when n tends to infinity, so this also becomes 1, right? And then now we can combine these two. So we can go ahead and say, because we have this and this, so we have n log n over n plus 1 over 3. And as you can see, if we divide across by n, so we have n here, so that as when n becomes too large, this really tends to 1, and so the log to the base n of 1 will be 0, so this becomes 0, and we said this tends to 1, and this tends to 1, right? And here, this is interesting because, again, we could separate it out so that we have log n of n, log to the base n of n plus 1 over 3 minus log to the base n of e, so that since this is a small constant relative to n, when n tends to infinity, that part goes to 0, and this part goes n base, same base, and also same number. So this would tend to 1, right? And so we have now a half, because a half times 1 minus a half, and plus 0 minus a third. So this and this would cancel. So we are left with negative 1 over 3 as our final answer. So this is interesting. This has been a very interesting problem. I hope you really enjoyed following along. Definitely knowledge of Stirling's approximation kind of seemed like the important principle that would enable one to connect it to the answer. So if you have any questions, if you have alternative methods on how to go about solving this problem, please, we welcome them. We do welcome those suggestions. Thank you. Until next time, at the local question forum. Yes.